So a lot of this unit is gonna sound familiar. We had a lot of the same information last year, in 8th grade science, and we're just gonna kind of extend and add to it. So we know that forces are just a push or a pull, okay? Even if you can't make the object move. So, if he's trying to pull that Humvee or Jeep or whatever it is, and he can't get it to move, he's still exerting a force. He just can't overcome the static friction between the ground and that object to get it to move. So just because you're not causing a push or pull doesn't mean you're not applying a force. And sometimes people get that confused a little bit. Force is going to be vector. So what does force going to usually include then?
Direction.
A direction. Okay, good. All right, so just like velocity and acceleration, forces are going to have magnitude and direction, which obviously magnitude is just a number. But the important part there is that it has to include that direction as well. And so a force is just a push or a pull, which is a pretty basic, easy idea. Okay. Some major types of forces are friction, drag, gravity, and lift. Obviously, friction is something that works against motion. Drag is a specific type of friction. Lift is the force of air pushing up on something. Those are some common ones that we'll look at. Right, so a pull-up, you have to apply force to make that happen. A push-up or a plank, right, you're pushing against the ground. Ooh, looks a little rough.
Looks fun.
Fumblerooski happening here. Looks like 26 is applying a substantial force.
26 is Gary. Gary's number 26.
Okay, so forces are going to have a new unit. A unit that we have not talked about yet. Are you done with your practice email?
Yeah, now I am.
Perfect. All right, thank you. Okay, so we measure force in the Newton. It is named after Sir Isaac Newton, right? And so we capitalize the N, right? So if you're writing the Newton, it is not a lowercase n, it is named after Sir Isaac Newton, a person, a proper noun, and so we capitalize it. We also make a capital N if we're abbreviating the Newton. It technically is a combination or a derived unit that is a mass times an acceleration. Kilogram, I know, is the unit for mass, and meter per second squared is a version of acceleration. So I know that it's a mass times an acceleration. And it specifically needs to be the kilogram and the meter per second, or meter per second squared, not like a centimeter per second squared or a mile per minute squared. It has to be these specific versions of mass and this specific version of acceleration, right? It can't just be the milligram or the gram. It's going to be a kilogram times a meter per second squared. That is what makes a Newton. It's a lot nicer to be able to use the Newton than to have to do a kilogram times a meter per second squared. That would be a mess all the time. And so it was nice that they combined that into a new unit that we call the Newton. Okay, this can be measured with a spring scale. Should have got one out. So a spring scale, you might have seen these if you do much fishing. You probably have one in your tackle box or possibly on your boat. You have a boat? Get that over here. Okay. If you do any grocery shopping, maybe you help do the grocery shopping in your family. So this is a spring scale where it's basically measuring the pull of gravity on an object. And so like if you go fishing and you catch a fish, they hang it from the hook and it pulls down, and how much it pulls down, that will give you the weight of that fish, okay? They also have these kind of spring scale systems like at the produce part of the grocery store. So a lot of times like there'll be like a bowl or a basket, and then it's connected to kind of a hook, And so when you put the fruit or the vegetables in that basket, it pulls down, and then that gives you the weight, okay? So those are just some common places where you might see that. So we can measure the force that something's pulling down, or the pull of gravity, which is a force, by using that spring scale. If you look at this football player kicking the football, what forces do you think are at work on that football? Gravity is going to start pulling it down, right? It's in free fall, or like it's in the air, and so gravity can pull it down. Actually, everything, even like, the spring scale, my baskets, all of us, we're experiencing the pull of gravity on us right now, obviously. Yes? Oh, I thought you were raising your hand. Yeah. What got this ball in motion? The kick, right? Good, the kick. Oops. So we see the applied force. So if we imagine that this got moving because he applied the force from his foot to the ball in this angle, and then like Brady said, force of gravity is going to be pulling down. These are the two forces that are actively working on this ball at this moment. This F means force, this little abbreviation means applied, and this abbreviation means gravity. So the force of gravity and the applied force. And we'll look at a lot of those. So here's some examples. Here's a real common one, a contact force. This is where, we had a whole unit on this. We had contact forces, and then we had a whole unit of forces that worked at a distance, like the magnetic and the gravitational. Contact forces, they're simple. There has to be a touch, okay? So if I'm just like pushing in the air, I have no contact. As soon as I touch the board and I push, that's a contact force. We also have an applied force. It's the force that is being applied to the object. We talked about normal force last year, and we'll get into this a little bit more this year as well. Normal force sounds like an easy thing, but it's so common that it's actually a little confusing, because you're like, what? Like, isn't that just the way it is? There is a little bit more to it, and so we'll talk about the things that are involved with normal force as we get to these specifics. Compression, forces that are squishing things together. So if I take a spring and I compress it, I have now applied a compressed force to it. And so if I let go, it's going to rebound or go back. There's something called a tension force, which is like a hanging or a pulling force. So somebody hanging from the monkey bars, right? They're dangling. That would be a tension force. A swing hanging from like the crossbar, that would be a tension force. So anything that's hanging, or even like if I'm playing tug of war, right? If I'm playing that, pulling that rope, I'm applying tension to that rope. That is called a tension force. And then friction is going to work against motion. And so there's lots of different types of friction, but drag is one where you're talking about an item that is moving through a gas or a liquid. Well, gases are all around us, right? We live in a gassy environment, right? Literally, last period, somebody was giving us a little extra gas, and I was like, what did you have for breakfast? It was rough in here. But normally, like, we have like oxygen, we have our air all around us. So unless you can remove that, everything is going to experience some form of drag that is caused by gas. If something is moving through a liquid, a boat moving through water, that would experience drag. So if the boat's moving this way, drag is dragging or pulling it back. So drag is just any type of object moving through a gas or a liquid, which is a very common occurrence here on Earth. Air resistance, again, is a special type of drag, which is a special specific kind of friction. Air resistance is going to be the resistance that the air causes. So a lot of these sound exactly like what they are and what they do. Okay? So air resistance is going to work against the motion. So air resistance is, as this person is falling, air resistance is working against them. Okay, here it's showing the friction of drag as the person is cutting through the air. So gravitational force, is also called weight, and last year we said gravity and weight both have the letter G in them. And so weight is the one that is affected by gravity, and we'll get into that more. We also talked last year about the non-contact force of electrical energy and magnetic. And these have to deal with charge. Right, so you can get something to move based on a buildup of charge. It wants to discharge and go back to neutral. We also know that opposites will attract, like a south and north, and that like will repel. Same thing with electrical, that positive and negative will come together, but two positives will push apart. So we had a whole unit on these three last year. Those non-contact forces, those forces that kind of work invisibly, kind of like voodoo almost, they seem like, right? So we already have a pretty good understanding of those. So again, there's a lot in this unit that is going to be kind of repeat, and then we add to it. Okay, so the normal force. This is the, again, I think this is a little bit one of the more confusing ones, just because it is something that we don't even really consider because it's so much a part of our daily life, right? And so this is going to exist between two solid objects when their surfaces are pressed together or in contact. So this book contacting this table, the book is experiencing normal force. Well, what force is pulling down on the book right now? Gravity. Good. So what we don't consider is that this table is actually pushing up on the book with the equal amount of force that gravity is pushing down. Right now, all of you are sitting down. Your behinds are in a seat. Gravity is pulling you down. It's not pulling you through the seat. It's not pulling you through the floor. It's not sucking you into the center of the earth because you are solid. The chair you're sitting in is solid. So solid to solid means that the normal force is going to push back up on that object with an equal amount of force as is pulling down. We don't consider that. It's not even something that we ever really consider until we come to science class. At least I know I don't. I don't know, maybe you guys are thinking more scientifically than I am on a daily basis. Don't know. But it's so much a part of our life that we don't even consider it, right? So there's a couple things that are you have to consider with normal force. The first is that it has to be a solid to a solid, all right? Like my book and this table. The other thing is it can also be, right, usually we're talking like horizontal, forces, but this can also be like a magnet sticking to a refrigerator, okay? So it can be kind of like that, a more vertical kind of attachment. Here's the other thing that is kind of like the main key. Normal force is going to work perpendicular or to an exact right angle to the surface that the object is on. So if this book is now my surface, it's like a hill, okay? This is my person, my little skier, okay? This is my angle, this is my slope, this is my ground, it's a solid object. Well, the skier is a solid object. His skis are in contact with that. This is going to be the angle of the normal force. Is it exactly vertical? No. It is going to be perpendicular, making a perfectly right angle with the ground. So if the ground was like this, then this would be the normal force. When you walk up a hill, which direction does it feel like you're being pulled? Thank you, Caden. He's like, down, right? You feel like you're being pulled down. Did gravity all of a sudden get stronger? No, the gravity is staying the same, but what has changed is that if gravity is pulling down, right? And my normal force is at an angle because the ground is at an angle, then the gravity and the normal force are not canceling each other out. If I have a perfectly flat surface and I have my normal force, it is going to be exactly equal to gravity. And so they're gonna cancel out. You're gonna get no change in motion. So you're gonna feel, like when I'm standing like this, I don't feel like I'm being pulled one way or another. I change my center of gravity, right, and I go crooked, now my normal force is going to follow the mass of my body. And so whichever side I'm leaning, that's gonna experience like that offset normal force. And so my normal force is not gonna be canceled out by gravity, and if I don't catch myself, I'm gonna fall. It's not that gravity has changed, it's just that the normal force is now perpendicular to the angle. So perpendicular, and if it's flat, perfect. Gravity gets canceled by the normal force. As the slope changes, my normal force angle changes, and it is no longer going to totally cancel out gravity, right? And when it's not canceled, then you're gonna feel like gravity has increased. Even though gravity is the same, it's gonna feel like it has gotten ramped up, okay? And so that's a huge thing. If it is at an angle, a right angle, whichever way the ground or the surface slopes, the more of a slope, the more you're gonna feel like gravity is stronger. So if you're just on a little bit of a slope, not a big deal. But if you're like this, it's gonna be really, really hard for you to keep walking up that hill because it's gonna feel like you're getting pulled downward, right? Because so much of the normal force is not getting canceled out by gravity, so gravity seems to win, seems stronger. But the two things, solid to solid. So if this book is in free fall, before it hits the table, is it going to be experiencing normal force? Doesn't experience normal force until it touches this table. Okay, so it has to be between two solids and it works at a right angle. Okay, and so we abbreviate the normal force, force norm. Okay, contact forces, this is pretty easy, right? It's the force that exists when there is direct contact. There has to be a touch. If there's no touch, then it's not considered a contact force. Those non-contact forces that work are gravity, right? Because there's not a hand. Gravity doesn't have a hand that's pushing down on you, right? It's just that invisible force at work. Magnetism is also going to work invisibly, right? Gravity's pulling my magnet down. Oops, too far away, right? I can't see that it's going to suck that magnet in, right? So those are working with non-contact forces, but all things that have to have a touch, like I can swing the bat as hard as possible, but if I miss the ball, is the ball gonna go and play? Probably not, right? Like I have to contact it, okay? So it has to be a touch. Without a touch, there's no contact force being applied. Now, there can be other forces that work on it, but there's no contact force. And if there's no contact force, then you're also not going to have a normal force because things have to be, a solid to a solid have to also be touching. So, you know, some of those forces kind of go together. Okay. And so an applied force is an outside contact force that is exerted or applied, and it usually causes an object to move in that direction of the applied force. Again, I can push. If I don't apply enough force, I can't get this table to move. If I apply enough, I can get it to slide, right? So just because you're applying a force and you don't get the object to move, it doesn't mean that you're not applying a force. It's just you're not applying enough of a force to overcome the static friction that's holding this table in place. Right? We represent the applied force with the abbreviation of AP. Okay? And so you can see he's applying a force in this direction. We use vector arrows again in this unit, like we did last year, and like we kind of introduced a little bit, just the direction idea last unit. Okay. Tension force. So if you have a rope that doesn't have any slack in it and you are pulling on each end in opposite directions, you are going to apply a tension force. This also works with hanging, so anything that is suspended or hanging will be experiencing a tension force as well. And we call that tens, so the tension force is tens. And again, that capital F is for force. Okay, so they're both pulling in opposite directions. And they're not causing any change, so I know that they're actually pulling equally and in opposite directions. So the diagram below shows two people having a tug of war, and so we know that the tension force is 900 newtons to the left, and we're trying to determine what the tension would be that person B is pulling. Well, I don't see any change. It looks like they're equal, right? And because they're pulling equal, that person would have a tension force of 900 newtons to the right. So tension is going to be constant throughout the entire rope because the forces are opposite but equal in force. If one of them was stronger, then the motion would occur in the direction of the stronger force, which kind of is logical. And again, we talked about all this last year, or you should have in 8th grade science. So this should not be something that is like new information. All of this we've actually already covered. Compression is a squish. So you have a spring, you have that compression gear. We know that compression, like gear that you wear for athletics, right, is to squeeze or pull in your muscles. It helps your muscles, stay warm. It also helps them not to kind of get pulled or stretched. Keeps everything compact. It's supposed to be, good to, keep you from getting strains and tears and things, right? So compression is a squish, squishing things together, and then tension is a pull. Both of these are considered contact forces because they're not going to work unless there is a touch. There has to be contact. So friction is going to be the force that moves opposite the movement between the two objects, or between the object and the surface. Okay, and usually it's going to point in the direction opposite to the relative motion of the object. So a pushing force is an applied force. I'm pushing to the right. Motion looks like it's going to be to the right as well. So if my motion is to the right, then I know friction is always going to work opposite that or to the left in this example. If I'm getting this object to move, then I know that my applied force, or that pushing force, is greater than the friction. If I'm pushing, but I'm not getting it to move, then I know that the friction is greater than my applied force. And we'll look at a bunch of examples of these too. Okay, so here's some kind of logic, common sense. We know that friction is going to be greater between rough surfaces. Okay, and there's a greater force between the surfaces, or when there's a greater force between the surfaces, like an object has more mass, it is going to experience more friction. So this table, if I push on this table with the same amount of force as I push on this book, I can easily move the book, right? Because it has less mass. I would need to apply more force to move this bigger, heavier table that has more mass, right? And so again, that's kind of a common idea. There's something called static friction that is the friction between the example of my table and the floor, right? I have to apply enough force to overcome that static friction to get the table to start moving. There's a lot less static friction between the table and this book because I can just give it a little push. If I do the same thing here, just give it a little push, it'll wiggle, but I'm not sliding the table all across the room like I can this book. Okay. And so we have three types of friction. Three categories, I guess. The first is static friction, and this is friction between two surfaces that are not moving past each other. Okay, so they are kind of stuck. So I'm applying a force. I'm pushing my table. I can't get it to move. Okay? Static in physics means not changing. If there's something that's in static equilibrium, it's an environment or a situation where there is no change taking place. So static in this case means no change in the motion. So if this table is not moving, it's going to stay not moving. Okay. So they are not moving past each other. I push a box, but it doesn't move because the static friction cancels out my applied force. Okay. Sliding friction is friction caused by sliding two surfaces past each other. They slide. So this book is experiencing sliding friction. I'm sliding it all around the table. So it is experiencing sliding friction. I'm moving it, so the applied force is more than that sliding friction, but what is at work on it, and if I give it a tap, it's gonna eventually stop pretty quickly. If I give it another little tap, right, it'll move until the sliding friction totally slows it down. So I push a box along a surface, the box moves in the direction you apply the force as long as you continue to apply it, or until the sliding friction overcomes that and it eventually stops it. Just like if I kick a ball, it's gonna roll across the floor for a while until eventually it slows to a stop. If I'm not continuing to apply that force, the ball is not gonna continue to roll indefinitely. And the rougher the surface, the more it will slow that down. Okay, let's go back. Let's go ahead, let's stop there.